Hello dear students, welcome back to chemistry class. It has been some time since our last class, and so I hope that all of you are doing well and studying hard at home. Last class we have learned some methods for preparation of haloalkanes. So today let us see some methods for preparation of haloarenes. The first method that we have is from hydrocarbons. Now remember that hydrocarbons can be used for preparation of haloalkanes also, but in that case we use aliphatic hydrocarbons. But for preparation of these haloarenes we use aromatic hydrocarbons, which are also called as arenes. Chloro and bromoarenes can be easily prepared by electrophilic substitution of arenes by using chlorine and bromine in the presence of a Lewis acid catalyst like iron 3 catalyst. So let us see some examples here. If we take an arene like toluene, this is C6H5CH3, we treat it with chlorine in the presence of a Lewis acid catalyst like ferric chloride. The reaction usually takes place in the dark. Substitution takes place at O2 and bara position. So usually we get a mixture of O2 and bara substituted products. So in the case of toluene reacting with chlorine, we get O2 chlorotoluene and then para-chlorotoluene also. Similarly, if we use bromine, if we treat bromine with toluene in the presence of this iron chloride, then we get a mixture of O2 bromotoluene and para-bromotoluene also. Now there are three important points to remember regarding this reaction. In the reaction we get a mixture of O2 and para substituted products. These two products can be easily separated because there is a large difference in their melting points. Usually the para isomer will have higher melting point, and therefore due to difference in their melting points, the O2 and para isomers can be easily separated. That is one point to remember. The other point to remember is that using these hydrocarbons we can obtain iodoarenes also. But in the case of iodoarenes, what happens is that we get only one product, and the other product will be hydrogen iodide. Let's see the example here. We take toluene again, treat it with iodine in the presence of iron chloride. The reaction once again takes place in the dark. Usually the para isomer will be formed here. So we get para iodotoluene, and along with this we get hydrogen iodide as a byproduct. Now the two products formed here, these two can react together to give back the reactants. That means the reaction is reversible here. Therefore, in order to stop the backward reaction from taking place, we use an oxidizing agent like nitric acid. The oxidizing agent, it will oxidize the hydrogen iodide that is formed, and therefore prevent it from reacting with this hydroarene that is formed. The third point to remember is that the fluoroarenes are usually not prepared by using these hydrocarbons because fluorine is very highly reactive. So please try to remember these 3 points. The first point, once again, the O2 and para isomers that are formed in this reaction can be easily separated because of difference in their melting points. The second point is that hydroarenes can also be prepared, but the reaction is reversible. Therefore, to prevent the backward reaction from taking place, we use an oxidizing agent. And the third point is that fluoroarenes are usually not prepared using this method because fluorine is very highly reactive. Now, the second method that we have is the preparation of these haloarenes from amines. So in the second method, we prepare these haloarenes from amines. This method involves 2 steps. In the first step, an aromatic primary amine is first converted into a diazonium salt. Then in the second step, this diazonium salt that is prepared is treated with cuprous chloride or cuprous bromide in order to obtain chloroarene or bromoarene. Let us see the 2 steps here. We take a primary aromatic amine like aniline the aromatic amine, it is treated with sodium nitrite in the presence of very cold dilute acid like HCl. On treating the primary aromatic amine with sodium nitrate in the presence of very cold dilute acid, we get a diazonium salt. In the next step, this diazonium salt is treated with either cuprous chloride or cuprous bromide. So if we use cuprous chloride here, the product form will be chloropenzene, and nitrogen gas will be given out as a byproduct. If we use cuprous bromide, then we will get bromopenzene. Now the first step, in which we obtain a diazonium salt from an aromatic primary amine, this step is called as diazotization reaction. And the second step, where we obtain either chloro or bromoarene from diazonium salt, this reaction is called as St. Meyer's reaction. The diazonium salts, they can be used for preparation of iodoarenes also. But in this case, we don't use cuprous iodide. We simply shake the diazonium salt with potassium iodide and we get iodopenzene. Now, if we want fluoroarene, instead of potassium iodide, we can use HbF4. This is called as tetrafluoroporic acid. So if we use tetrafluoroporic acid, then we will get a boroarene. So these are the two important methods for preparation of haloarenes. One is from hydrocarbons and the other method is from amines. Now let us look at some physical properties of these haloalkanes and haloarenes. If we look at their physical state, we can find them in the gaseous state, in the liquid state, as well as in the solid state. Usually the lower members are found in the gaseous state. Higher members are found in the liquid state, while still higher members with higher molecular masses are found in the solid state. Many of these haloalkanes are colorless in the pure state, but the bromides and iodides, they develop color when they are exposed to light. And many of these haloalkanes, they are sweet-smelling compounds. Now the fourth property, which is very important about these haloalkanes, is that the boiling points of the haloalkanes are higher than the hydrocarbons from which they are derived. Let us try to understand it with this illustration. Suppose we have a hydrocarbon CH4, this is methane. From methane, we can obtain chloromethane. We can also obtain bromomethane. We can obtain iodomethane also. These are the halogen derivatives of methane. All these halogen derivatives of methane are found to have higher boiling points than the parent hydrocarbon, that is methane. Now there are two reasons as to why these haloalkanes have higher boiling point than their parent hydrocarbons. The first reason is because of higher molecular mass. Let us just see in this example. In methane, the carbon atom is bonded to 4 small hydrogen atoms. In chloromethane, it is bonded to 3 hydrogen atoms and a large chlorine atom. Here we have a bromine atom and here we have an iodine atom. All these halogens have higher molecular masses than hydrogen. So these molecules, these haloalkanes, they have higher molecular masses than the parent hydrocarbon. When the molecular mass is more, the van der Waals forces of attraction will be more, and therefore boiling point will be higher. The second reason is because of higher polarity. In fact, the hydrocarbons, they are non-polar molecules, while the haloalkanes, they are polar in nature. They are all polar molecules. So the intermolecular forces of attraction in these haloalkanes are dipole-dipole interactions, whereas in hydrocarbons, the intermolecular forces of attraction are the weak van der Waals forces only. So these dipole-dipole interactions that are found in the haloalkanes being more stronger than the van der Waals forces, the boiling points of these haloalkanes will be higher than the parent hydrocarbon. There are some important points again to remember regarding these boiling points of haloalkanes. Let us see some of them. The first point is that if we have some compounds having the same halogen atom but different carbon chains. Suppose CH3 Cl, then CH3 Br and CH3 I. Okay, in this one we have the same alkyl group, not the same halogen atom, the same alkyl group but different halogen atoms. If we have compounds like this, the molecular mass of the halogen will determine the boiling point. The higher the molecular mass of the halogen, higher will be the boiling point. So among these three, iodomethane will have the highest molecular mass and therefore the highest boiling point. Then comes bromomethane, and then chloromethane will have the lowest boiling point. Once again, if we have the same alkyl group but different halogen atoms, the boiling point increases with increase in molecular mass of the halogen. The second one, if we have the same halogen atom but different alkyl groups, suppose we have chloromethane, then chloroethane, then chloropropane. These three have the same halogen atom but different alkyl groups. In such cases, the boiling point will depend on the length of the carbon chain. The more the number of carbon atoms in the molecule, the longer will be the chain length, and therefore the higher will be the boiling point. Why? Because when the chain length is longer, the surface area of the molecule is more. When the surface area is more, the magnitude of van der Waals forces also increases, and therefore boiling point will increase. So in this case also, this one will have the highest boiling point and chloromethane will have the lowest boiling point. The third point to note is that if we have isomeric haloalkanes, then the boiling point will decrease with increase in branching. Let us see one example here. Here we have 1, 2, 3, 4, 5 carbon atoms. So this will be chloropentane, 1 chloropentane. Then we take another compound. Here also we have 5 carbon atoms, but here branching has taken place, branching on one side. Then in another compound, once again we have 1, 2, 3, 4, 5 carbon atoms and 1 halogen atom, but here branching has taken on both sides. Now when such branching takes place, the surface area of the molecule decreases, and when the surface area of the molecule decreases, the magnitude of van der Waals forces of attraction decreases, and therefore the boiling point will decrease. So among these three, this one where there is no branching will have the highest boiling point, this will have the next, and the one where there is the most excessive branching will have the lowest boiling point. Then the fourth point to remember is that if we have isomeric dihaloarenes, let us take 3 isomeric dihaloarenes where the chlorine atoms are placed at different positions. The first one is ortho-dichloropenzene. The next one is meta-dichloropenzene, and this one is para-dichloropenzene. When we have isomeric dichloro or dihaloarenes like this, their boiling points are almost the same, but the melting points are different. The para isomer will have higher melting point than the other two isomers. The reason is because the para isomers, they are more symmetrical. Their molecules are more symmetrical, and being more symmetrical, they fit more closely in their solid crystal lattices. The more the closely packed structure, the higher will be the melting point. And it is for this reason the para isomers will have higher melting point than ortho and meta isomers. That is all for today. We'll continue in the next class. Thank you.